This is Viterbi Voices, your chance to hear stories about research, classes, student life, and more.
Directly from our students, faculty, and other members of our engineering community. All right here at the USC Viterbi School of Engineering.
Welcome back into Viterbi Voices. This is another bonus episode and faculty roundtable. I am one of your hosts. My name is Paul Ledesma, Director of Undergraduate Admission at the USC Viterbi School of Engineering. We're going to be throwing a lot of these episodes out at you pretty quickly here over the next couple days, and as such, it's just going to be me on the intro. Audrey's still doing well. She's in Colorado. But for our admitted students, we've been hosting some faculty roundtables with different academic departments as we've scheduled them independently with faculty from each of them, and bringing in a lot of our admitted students to Zoom calls to chat with them and ask questions. And we thought it would be helpful to take that audio and throw it up here on the podcast so that everybody can enjoy it. So today, we are bringing you the faculty roundtable for the Aerospace and Mechanical Engineering Department. We have three fantastic faculty, Dr. Matthew Gilpin, we have Dr. Charles Radovich, and Dr. Paul Ronney. Now, the audio is a little dicey on a few of them because they had some internet connection issues. And I want to point out right now, if you see the video, we'll probably put it on YouTube as well, that I don't know how else to say this, but Dr. Ronney has a horse in his video, and you can hear the horse every once in a while. Sometimes when someone else is talking, sometimes he references the horse. The horse's name is Junior. I was laughing hysterically the whole time because he was talking about some serious stuff, talking about his research in combustion, and all of a sudden you hear a horse neigh in the background. So it's quite entertaining. And I think what that shows is that our faculty are doing everything they possibly can to be as entertaining as they can when they're doing the remote classes. I know that Dr. Ronney, when he's teaching, he sent us a couple images of this. He's teaching, heat transfer, and he's got a whiteboard and his horse is right next to it. I mean, it's hilarious. Anyways, that's what's going on. We're going to give you this episode here. It's about an hour long. It's a great discussion about aerospace, mechanical engineering, the classes, the overall curriculum, the theoretical work, the hands-on work, the research that goes on, and then specifically kind of what they think is important to them. So I'm going to get out of the way. I'm going to let them take it over. And if you're an admitted student, you got more questions for us, give us a holler. We'd love to hear from you. And yeah, that's it. All right, y'all. Here you go. Aerospace and mechanical engineering. Hello, everyone. Hello. Welcome to the Faculty Roundtable for the Aerospace and Mechanical Engineering Department. My name is Paul Ledesma. I'm the Director of Undergraduate Admission at the Viterbi School of Engineering. I'm muting you right now. My name is Paul Ledesma. I'm the Director of Undergraduate Admission at the USC Viterbi School of Engineering. Welcome to the Faculty Roundtable for the Aerospace and Mechanical Engineering Department. With us today, we have three faculty members. I'm going to let them introduce themselves here in a second. And they're going to talk a little bit about who they are, obviously, what they do in the department, maybe classes that they teach, research that they conduct, and overall just give you a sense of who they are. And then I'll start asking some questions in general so you can get a sense of what aerospace and mechanical engineering is all about at USC in the Viterbi School. And then toward the end, get your questions ready, because then I'm going to open up the chat for all of you to go ahead and ask questions into the chat specifically. And I will moderate that as kind of like a talk show opportunity for you all to get those questions in. But hold those questions now until we get to them. But I'm so excited that all of you are here. Without further ado, let's introduce our faculty. We'll start with Matthew Gilpin.
Sure. So I'm Matthew Gilpin. I'm a senior lecturer at AME. I teach our mechatronics class and our senior projects. So you'll all see me when you're upperclassmen. I'm also faculty advisor for our human-powered vehicle, which competes every year in the ASME Human-Powered Vehicle Challenge. And I'm also a faculty advisor for APP, which is our Advanced Spacecraft Propulsion and Energy Laboratory, with the intent of giving students some hands-on experience on pretty advanced topics. I've been at USC for 5 years as a lecturer, and my background is actually in spacecraft propulsion, particularly micropropulsion, also solar energy and concentrated solar power are the things that I have a background.
That's great. Thank you, Matthew. Let's go with Dr. Ronney.
Okay, hi, I'm Paul Ronney. I'm a professor of aerospace and mechanical engineering. I've been at USC since 1993, and I'm fortunate that I have a place to go to stay socially separated. The barn, this is actually not my horse here. This is another one. My daughter has our horse out right now. This horse here is, his name is Junior. Let me see if I can get him over here. Junior. I'm gonna get him.
So we didn't promise horses, but we deliver on horses, and that's where this stands apart. We actually have a horse, and the horse is, to be clear, Dr. Ronney, the horse is not on faculty in the Aerospace and Mechanical Engineering Department, correct?
Not yet. So I teach, among other things, the Introduction to Mechanical Engineering course. So if your son or daughter comes to USC and chooses the mechanical engineering option as opposed to the aerospace engineering option, then he or she will see me in the very first semester. I like to say that that course is sort of a boot camp for engineers. I try to go over some fundamentals, units, and scrutinizing your results. There's also, and then talk just in a little bit of detail, very, very top level, a little bit of detail about some of the major courses that you would take as a mechanical engineering major: structures, statics, fluid mechanics, heat transfer, thermodynamics, etc. There's also a laboratory component where you learn how to use SolidWorks, that is a computer-aided drawing program. And also there's a couple of small group projects, one involving robotic cars and another involving 3D printing a bridge and seeing whose bridge can hold the most weight.
That's great. Thank you very much. And last but not least, Dr. Radovich.
Hi, everybody. My name is Charles Radovich. I'm a professor of practice in the Aerospace Mechanical Engineering Department. The courses I teach have included Intro to Flight, so the freshman level course, although I'm not teaching that this upcoming year, sophomore level flight mechanics course where we discuss how to conceptually design aircraft, understanding performance and wing sizing, all the way to internal layouts and basic configurations and seating arrangements. I teach a lot of lab courses, so a lot of junior level and senior level labs, hands-on projects, senior design projects. And I like to involve myself with as many of these student design teams as I can. I'm the faculty advisor for the aero design team. I co-advise Aspen with Dr. Gilpin, which you mentioned before. And beyond that, any design team that's having a design review or I can help out, I'd like to do so.
That's great. Again, for everyone that's in our audience, please hold your questions till we get to the end, and then I'll have an opportunity to open that up and we'll get to your questions. But to start us off, whoever would like to jump in here from our faculty, can you give an overview of the discipline? Maybe we'll have someone talk about aerospace engineering or someone talk about mechanical engineering, and maybe we can discuss the differences between the two. I think that's one of the first things we should talk about because your department handles both aerospace and mechanical engineering, and we have students in the room that have been admitted to both. Charles?
Sure, yeah, I'll chime in on the aerospace side of things. And more or less, I think, rather than a hyper-focused discipline, I think the general discipline that we become is problem solvers and ones that understand nonlinear systems that require a lot of groups to come together and pull together a solution. So that becomes very useful in, say, the rocket world, where you have structures and propulsion and aerodynamics coming together, and we're kind of that skill set that can generally understand bits and pieces from all of those areas. For myself personally, it's become a life of understanding fluid mechanics, and that's just how does air or water or any sort of fluid surround something that's moving through that medium. So it could be related to boats, or it could be water droplets coming off of car tires, which is something I actually researched, as random as that sounds. But there's connections with droplet production that I could have bridged over into the combustion world as they spray fuels, parlayed that into an external aerodynamics consulting career with SpaceX for launch vehicle design, Dragon mission design as well, and spacecraft reusability. So it could really be whatever you want to make of it if you understand the general discipline that you have and the different ways you can contribute.
All right. And what about mechanical engineering? More specifics on mechanical? Maybe Dr. Ronney? Yeah, go for it.
Yeah, as I say in my freshman class, mechanical engineering, every department says that their specialty in engineering is the broadest department, including mechanical engineering. However, in the case of mechanical engineering, it's actually true. So what I like to say is that if it doesn't involve things that fly, in which case an aerospace engineer will handle it, doesn't involve life forms, in which case a biological or biomedical engineer will handle it, doesn't involve large structures, in which case a civil engineer will handle it, doesn't involve electrons, in which case an electrical engineer will handle it, or it doesn't involve materials, in which case a materials engineer will handle it, then a mechanical engineer will handle it. Oh, by the way, if it has any of those things, a mechanical engineer will probably be involved anyway. And I like to say that because a lot of the things that we cover sort of span all disciplines. Just as one example, I could give many, but I'll just give one, is that heat transfer is one of the core subjects of mechanical engineering. Now, heat transfer, I admit, is not really that exciting a topic, even though it's sort of in my wheelhouse. But all engineered systems have issues with heat transfer. And if you don't pay attention to them, they'll come back to bite you. Just as for instance, a lot of students, they go to work on whatever project. Their first day on the job, the boss says, well, we have a problem. Our biggest customer says that our system is overheating. Do you want to think about heat transfer? And so if you're able to then say, well, yeah, I know a little something, let me take a look at it, that makes you then more valuable to the team. So again, things like heat transfer, as fluid mechanics, as Professor Radovich mentioned, structures, all those are sort of within our wheelhouse. And I say all engineered systems have issues with those.
Thank you. Now, a lot of students also we'll try to figure out, okay, that's all great, but what's the best one? And I don't want you to answer that question because I don't want to get a fight going. But I think
not a fight.
But I think that what might be helpful as well is to help explain how aerospace and mechanical engineers have a lot of similar and overlap inside their curriculum, and they end up working together and sometimes doing some of the same jobs regardless of the undergraduate degree between those two. Can we talk a little bit more in depth about that?
Sure. I describe it to people as it's like a funnel of specialization. So in my own career, in my experience, I work with aerospace engineers, I work with mechanical engineers, I work astronautical engineers, and they're all working on the same tasks. But as a education, as you approach USC, I would think about it as mechanical engineering is the most broad, right? And so if you're interested in planes, you're interested in cars, you're interested in manufacturing machinery, all of those things, you're going to learn the same principles in mechanical engineering degree, but it's going to be a lot more broad application. But if you're coming to USC and you know that you're married to aircraft or you're married to aircraft, then the aerospace side of things teaches a lot of these same principles, but will do it under the lens of aircraft, or will do it under the lens of spacecraft. And you'll have these specific problems related to that application as opposed to a more general background. And so with both, with a mechanical degree, you can definitely do, aerospace work, you work in spacecraft, work in aircraft. But in terms of your experience at USC or your education, you'll just have a broader a more specialization in the application of your courses. But a lot of principles remain
the same. Anybody else want to jump in there?
Yeah, I was going to agree with that, and just wanted to hit on the point that I know a lot of times the worry is that aerospace is so specialized that people are worried to go that route. But the aspects of aerospace that are booming now go from micro flight, talking about insect level and small UAVs, all the way up to the largest transport aircraft, to hypersonic flow, to launch vehicles. There's an incredibly wide spectrum of problems out there. Amazon drone deliveries, for example, wind turbine and reusable energy, underwater energy power generation. It can be a world in aerospace that has nothing to do with things that fly. It's just relying on a lot of those same principles. So I don't want anyone to think that aerospace engineer means airplane, because there's a very good chance you'll never come close to an airplane, just with the number of job possibilities that are out there right now.
Thank you.
And I can speak to my own experience, and as I went to school as an aerospace major, and my thought was I'm going to work with planes. My life took a total 180. I ended up working basically purely spacecraft, and then rockets that are about this big, as opposed to things like SpaceX, etc. which I'm doing with an aerospace degree. I actually got I got a PhD in aerospace engineering, but my aerospace engineering PhD was 90% mechanical engineering and 90% heat transfer and energy analysis of these things. And so that title doesn't necessarily matter so much as, what are your interests and what do you explore? Because again, it's a broad field and you're learning the same skills.
Thank you very
One of the differences might be if you're going to learn about forces and moments, you could do it staring at a beam or put it into context of an aircraft.
That's great. I always like the subtle jabs at other disciplines that always come up in these. There's always a subtle jab at another area of engineering.
Oh yeah.
Can we talk a little bit about the curriculum in general, or as specific as you'd like to get? What can a student expect through the curriculum as they go through their first year, as they go through those middle years and their senior year, as they kind of evolve through theory and hands-on work? They will get the capstone courses. And just so that you know, all of our admitted students should have copies of our undergraduate handbook. And so if they're looking along, they can see the course plans. But if you can kind of share with them what to expect of their undergraduate coursework.
Okay, I'll handle that.
Sure.
So as I was telling Junior just before we came on the air, that you typically start out with a introductory course, whether it be 101, the course that I teach, or 105, the aerospace equivalent. And then there's, of course, the basic math, chemistry, and physics, chemistry or material science. And then typically then in your second year, you sort of start on what we call the sort of engineering science or engineering core courses. That's things like structural mechanics, fluid mechanics, heat transfer, statics, linked materials, control systems. And then as you progress to your junior year, then one of the courses that you take is this junior level lab course called Mechoptronics. The course that I say is always, whose 341 is always preceded or followed by an expletive, but it's an extremely important course. It's challenging for the faculty. I don't teach that, but for the faculty that do, it's extremely challenging. It's extremely challenging for the students as well. But I think it's one of the things that kind of sets our program apart from some of the others, is that it's a really intensive hands-on course where you really learn about how to measure things and how to control things. So I think it's an essential aspect of our program. At the senior level, of course, there is most of the people out there probably know, you take a capstone course, which sort of summarizes all the things that you've done, and it's working towards some sort of a project. There's also a senior level projects laboratory. So the capstone course is typically, a design course, and there's separately a senior level 441 projects oriented course. One of the things that I think is advantageous about our program is that you get a laboratory experience virtually every semester that you're here. Like even in my freshman course, you have sort of 1.5 lab experiences. There's the graphics lab part, and then there's the hands-on projects part. And that continues throughout your entire 4 years. Now, at the beginning, students say, oh, wow, that's great. And then all this hands-on experience. What they maybe don't realize is that those hands-on courses, whether it be computer-aided drawing, whether it be computer programming courses, whether it be actually building and testing or laboratory courses, those courses take a lot of time, don't they? They take a lot of time, and in fact, if you probably were to look at the hours spent versus the grade points earned, it's probably a lot lower than that of your basic lecture, homework, and exam type courses. So be careful of what you wish for. But if you're wishing for that, I think our program is a good one to look at.
Yeah, for sure. There's a lot of learn by doing that's emphasized here. And that extends beyond the classroom into the design team world and into our research labs, which I think are the other, Mechoptronics was mentioned as kind of like a core asset of this department, but our design team and research culture is also a huge part of the students that, that graduate from here and are able to contribute in industry immediately, able to get internships and make flight parts as juniors and sometimes even sophomores. Yeah, to kind of address, I see Parth put up a question there, like what's the split of theory and hands-on learning? There is certainly a mix of both. We ensure that everybody gets a dose of both of those things. By your senior year and a little bit into your junior year, you'll have the ability to pick your upper division courses to align more with your particular interests. So if you want to do a lot more of the theoretical or computational work, you could go that route. Or if you find out that you really enjoy the experimentation side of engineering, you can choose your upper division electives to sit in a laboratory setting.
Thank you.
And,
Matthew.
and I can touch a little bit on design teams. If we were doing a in-person explorer, I would end up taking you on a tour of some of these student design labs. And with the classes, you're learning theory, you're learning application, but where we've grown over the 10 years that I've been involved at USC, where we've grown so much of these student design teams that give everyone the opportunity to get this hands-on experience and touch hardware. And so we have Formula SAE, where you're actually constructing a race car from scratch that goes in races. Or if you're in a human-powered vehicle building these recumbent bicycles, you can join Rocket Lab, where you're building actual rockets. You can join Aspen, where you're doing research. All of these design teams are open. They allow you to get hands-on experience. And what I'll typically tell students coming in is, say they want to work at SpaceX or Blue Origin or Tesla or any companies, the way to punch your ticket to do that is to get involved in these design teams and do this hands-on work, right? If you graduate and you're president of Formula SAE, you can punch your where you want to work. And the reason why is they know you have this hands-on experience. You have the theory, but you've actually touched the hardware. And so there's huge opportunities for that. We're opening up a new bomb makerspace, which is a facility specifically designed to allow these student design teams to manufacture professional quality parts. We're linked up with sponsors that allow us to do this. We actually just got for human-powered vehicle, we just got a new sponsor for our aerodynamic fairing. And as I'm picking it up from the company, they're telling me that this is the exact same quality carbon fiber they would deliver to Porsche for their aerodynamic packages. So very real, very applied, hands-on stuff that can be done in these design teams. And then a thing that I want to mention about our senior projects, so this capstone class that was is at USC, the way we run our senior projects is a little bit different than a lot of other universities. Our capstone project is completely open. And so we allow you to propose your own project. We give you the tools, funding resources, machine shop time, et cetera, to build what you want. And we basically say that, as a senior, you're applying for jobs. The best way to demonstrate your interest is, going to that interview and saying, look, I did this, right? And we want to give you that opportunity to actually put that to so something unique about our capstone environment in AME that we're particularly proud of and gives a lot of opportunity.
I wanted to add something about the design team cultures. They're basically like a bunch of, each of our design teams, we have a lot of them. There's a human-powered vehicle, which is a recumbent bicycle. There's a combustion-powered car. There's an electric car. There's a solid rocket team, a liquid rocket team. There's an airplane design team. There's an underwater robotics team. There's a spacecraft energy propulsion team. And there's always seeming to be another one coming out of the woodwork. But the special thing about them is the students have full ownership. And so while there are faculty advisors like myself and Dr. Gilpin here, the last thing we will ever do is tell them what to do with their team or how to run it. We're there to advise and to guide and make sure they're safe and present resources for them. But when they decide, say for the SAE racing car, that they're going to have a certain aerodynamics package or that they're going to have wheels of this diameter, or they're going to tune their engine in a certain way, that was fully of their design and their thought process. So they have full ownership. And this, in our opinion, is what really makes good engineers, is when you show up on the workplace, you know how to make decisions. You know how to quickly test things to see how they're going to work, to see if it's going to fail so you have time to recover. But ultimately, you can just take full ownership of that and be the best engineer possible. So a lot of pride in the way those teams are run.
Absolutely. And they've been very successful lately, too.
Oh, for sure. Rocket Lab, no doubt. Everyone's seen them in the news of breaking the student altitude barrier. Completely student designed. every last bit of it, from the diameter of that thing to the amount of rocket fuel to the actual type of propellant they chose to create, and mix that up and tested it over several years. Took a lot of work, but it was all their work. So it's very impressive to see that type of work.
Yeah. And can each of you or one or whoever would like to jump in, talk a little bit more about the research areas that are being done, or certain research projects that are being done with aerospace and mechanical engineering? Yeah, Paul.
All right. Well, you know how a lot of kids go through the stage where they make things burn or explode? Well, I never really grew out of that stage. And so now I make a living doing combustion research. So although it's somewhat ironic that the research that I do now is mostly looking at the sort of limits to combustion. That is, one sort of area that I work on is combustion at very small scales. The interest in that being to replace batteries with fuel power devices to generate electricity. Because as I usually start out when I discuss this topic to a live audience, I'll say, who flew, to be here today? And somebody will raise their hand. I say, did you fly here in a battery-powered airplane? And they say, no, of course not. I say, well, why? They say, well, because the fuel has much more energy per mass than batteries do, which is entirely true. And then so I say, well, do you have a cell phone? I say, well, yeah, of course. And they say, well, does it have fuel in it? They say, well, no, of course not. I say, well, why not? The fuel has much more energy per mass than the battery does. So why don't you use fuel in your phone? And so they sort of scratch their head. And the answer is basically we don't. The same thing we do everywhere in the world, every day at large scales. That is, convert hydrocarbon fuels to either shaft power or propulsive power or electrical power. We don't know how to do that very well at small scales. And because some people have tried just taking something let's take something big that works well and make it really small, like an internal combustion engine. They work fine at large scales, but when we try to scale things down, it just doesn't work because the heat losses and friction losses, they're not so important at large scales. They're important, but not dominant at large scales. They really kill you at small scales. So we've been looking for other ways, other than just scaling down big devices, to try to generate electrical power at small scales. Another aspect of that is also making robotic insects, as the other factor mentioned. And we haven't got insects that fly yet, but working with Professor Perez Arancibia, who's a robotics expert, I'm not in any way a robotics expert, they've been able to get beetles, basically fuel-powered beetles, that are totally autonomous. They do not have any electrical power or battery or anything like that. It's totally fuel-driven. They will crawl. Another aspect of that, talking about the propulsion side, is trying to make very small, basically rocket propulsion systems for formations of satellites. One of the hot topics in the aerospace business nowadays is clusters or formations of satellites. The analogy I like to use there is, most of you have seen the movie Finding Nemo. Well, you know the scene where all the fish kind of keep rearranging themselves into different patterns. Well, that's one of the things we'd like to do with satellites for different purposes, either for Earth observations, for communications, for spying, for radio astronomy. We'd like to be able to rearrange these satellites. One of the problems we have in doing that is that the amount of fuel we can carry in these small satellites isn't that much, and the efficiency of propulsion at those scales isn't that much. So we're trying to find ways to produce more efficient propulsion systems for these small satellites. They call them typically microsatellites or nanosatellites, which makes you think that they're smaller than a grain of sand. They're not. They're typically, there are many different ones, but maybe about this size, something like that, but they're called microsatellites typically. And one of the interesting things that we found is, you've all seen that the typical shape of a rocket nozzle that has kind of that hourglass or bell shape. Well, it turns out that's really not a very good design. It's fine, of course, for large scales, but at small scales, the optimal design actually has several additional wiggles in it. And if you don't put those wiggles in, you actually don't get nearly as good a performance as if you do. So those are some of the things that we're working on. This is all propulsion or combustion now at small scales. We're not trying to, make things more powerful, explosive or anything, which was kind of my main goal when I was about 12 years old. Half the things I did when I was, a teenager, if I did them nowadays, you'd have the black helicopters circling overhead and FBI and Homeland Security. Back then I was just, it's a kid down the street doing something else crazy. I still have all my fingers and see out of both eyes. So I say I never blew up anything I didn't intend to.
You put your evil to good use, so that's good to know. Other types of research going on in the area?
Yeah, so some other research I'll hit on is on the fluid structure interaction side of things. That's the name of one of our labs, and that's, as the name describes, how do fluids and structures interact? And some examples of that are using a water channel that we have, just understanding different coatings that can be applied to reduce drag on given devices. Some very interesting work happening over there. Also, keeping with this idea of smaller scales, our wind tunnel research group has focused many years now on bird flight. And there's a couple of reasons for that. There's this idea of learning from nature. How exactly do birds fly? And why don't they have a vertical tail, for example, when every aircraft we've ever designed has a vertical tail? Apparently it's not actually needed. So what is it that birds know and do that our aircraft don't do? So that's one of the thoughts. But there's also this huge surge in unmanned aircraft and small UAVs, in which case some of this small scale, what we call low Reynolds number testing, is starting to be very important for understanding the flight mechanics over there. Also in the aerodynamics or the aircraft design world, there's a lot of computational and numerical work. So you can work in a research lab that actually doesn't have the hands-on research component, but it does a lot more of the numerical analyses, whether it's computational fluid dynamics or just aircraft optimization and writing tools for sizing aircraft.
Fantastic. Before was something else to add in? Oh yeah, Paul, go ahead. Sorry.
Yeah, so just one little anecdote I'd like to add to what Professor Radovich said is that some years ago, we had a faculty member by the name of Fred Browning who was using that water channel, and he was studying the fluid mechanics of platooning of trucks. That is, if you have trucks, following one another very closely, drafting each other, as I guess you could call it, that the whole platoon can have less drag, total drag, than if they were separated. And so, for very good engineering reasons, he was doing experiments not in a wind tunnel, because we don't have a wind tunnel big enough to fit a full-size truck, but because of the way scaling works out, you can get effectively the same size in a much smaller physical space if you use water as the fluid rather than air. So I would take visitors around to the water channel, and they would see, these models of trucks in the water channel. And these visitors were scratching their heads saying, well, you planning to drive to Catalina or something like that? Why are you measuring the drag of the water drag on trucks? Now, does people know fluid mechanics? It makes perfect sense. If you don't, it makes, of course, absolutely no sense whatsoever. So that's actually one of the things that I talk about in my freshman class and many other classes, talk about this whole issue of scaling. I'm very fond of saying, if you don't understand the scaling of a problem, you don't understand the problem. That is, what happens if you double the size, double the speed, use a different fluid with a different viscosity. If you can't at least roughly predict what's going to happen when you make that change, then you really don't understand the problem very well.
That particular truck problem I actually got to work on in some of my graduate work here at USC. I was at the point where they had already studied the fundamentals on a smaller, cheaper, testable scale in these water channels. And so I got to work on the full scale version of that. So we were at the point where in these commercial trucks with trailers driving up and down a runway, measuring their fuel consumption in real time, and doing that as a function of distance. So I was in the trailing truck, and so all the way down to 3 meter spacing behind another commercial truck and trailer at highway speeds. It was kind of scary. But what was cool to see that work actually nowadays is actually getting utilized. And Anheuser-Busch put out some demo a couple years ago. They're kind of proposing, this is a large distributor, proposing using their trucking line in tandem so they can save fuel economy as they leave from Missouri to wherever, if they just sent out essentially like a train's worth of trucks to deliver. So it's kind of cool to see that work come around full circle.
Yeah. Well, that's great. I'm going to give our audience a kind of a 2-minute warning here. They can get their questions ready, and then we'll all open up for questions. But one last question from me for each of you. Our students they've just been admitted to the school. They're in high school right now. We're trying to wrap up those years, and they're trying to determine which university they're going to go to. And they have lots of great opportunities in addition to the Viterbi School. And so would you mind sharing, each of you, your academic backgrounds, like where you went to college, what you did, how you found yourself at USC, and because everyone has a unique path. So Professor Gilpin, why don't we start with you?
Sure. So I'm from Seattle, and actually went to USC for my undergrad and my master's and my PhD, and now I teach there. So including all that, I've been at USC for a while, and my path is actually a little interesting. I didn't necessarily think about Southern California, being a person from the Pacific Northwest, and I came to USC because they gave me a big scholarship, and it was the option that way. That was extremely fortunate, because it turned out, and I didn't realize this at the time, that Los Angeles is in fact the center of the aerospace universe. And so as someone that was at the time, obsessed with planes and rockets, these things, I couldn't have picked a better place. When I was a student at USC, my original goal was to go sit in a cubicle at Boeing after I graduated 4 years. And I ended up getting a job as a freshman in a research lab, and absolutely fell in love with it. I couldn't imagine doing anything else. Through that, I ended up with a couple of internships. One of those internships ended up being with the Air Force Research Lab. The Air Force Research Lab said, hey, if you go to grad school, we'll pay for it. And so I ended up going to grad school, and they said, if you get a PhD, we'll pay for it. And I said, of course. And lo and behold, I completed that. For a while, I was running a small research lab on campus. And I still actually maintain a relationship with the Air Force Research Lab, doing work with them over the summers. And now I'm teaching at USC. So a absolutely amazing path to put me where I am now. It was not necessarily what I had planned, but I really got to experience. You'll hear a lot of people talking about Trojan family and all these things throughout your application process, all these events. But I'm an example of someone who dramatically benefited and got to see that in practice. And what I'm actually finding right now, an interesting anecdote is, about 10 years ago, I was working in a research lab on campus called the Collaborative Housing Facility. And a month or so ago, I ended up doing a little bit of consulting work for a startup up in the area. And I walk in the room, and lo and behold, there's 3 other people that worked with me at USC in this propulsion lab on campus. And it turns out that the person that ran it, they had all gone to PhDs at universities, but it turns out the person that ran this startup had accidentally hired 4 people from the exact same year in the exact same lab, all from USC. So the world is really small, and you'll find that everywhere you go, there's a pile of USC people working.
I would echo almost that exact same story. I came to USC pretty naive about what engineering was in general, let alone aerospace engineering. Had no idea what I was in for. If there was one thought, it was going to be working at Boeing or something like that as well. I just didn't know what opportunities were about to show up, and they came very heavy. The amount of opportunities for whether it was research or working in industry just kept coming my way as a function of being part of this Trojan family. It's kind of very thankful for all of that. I started working in a wind tunnel in graduate school, just as, when I graduate, I would have that opportunity. And then I got an opportunity to work on my PhD and started working at SpaceX towards the end of that, just again, so I had work lined up for when I finished. And when I finished my PhD, I got a full-time offer to teach at USC. And my 3 degrees, bachelor's, master's, and PhD, were all done at USC as well. So that means I've been on this campus for 21 straight years, which I think just attests to how much I love being at this place. And now to be able to teach and contribute to the same type of experiences that I was able to receive just really makes it all worth it.
And I want to mention, to touch on that, the opportunities that both Dr. Rich and myself talked about at USC's campus. We're talking about engineering and things. I also want to touch a little bit on the opportunities that USC offers outside of engineering, and the things that you can get involved in as a student, and the resources that USC puts into this. In my experience at USC, I I was a marching band guy. I was at USC. As a result of that, as a student, this is all because I was involved and because I cared about it, not paying for anything. I got to go to every Pac-12. Well, at the time it was Pac-10, or sorry, but I got to go to every Pac-10 stadium and go to a football game. I got to travel across the country for basketball. We got to go to China for a World's Fair, and I'm performing on stage with Harry Connick Jr. in China. Through research opportunities on campus, my first business trip was to Hawaii, and second business trip was to France. So unbelievable stuff.
Really
Yeah, exactly. Well,
Yeah.
just unbelievable things that I got to experience by being part of this USC universe. And to like what Dr. Radovich said, when I came to USC, I had my family's not engineers, my parents aren't engineers, and I just had no idea what was out there. And just every single day, something new was unfolding, something exciting was unfolding.
I think it's important to add to that involvement and just interested aspect of our students and what makes up a USC Trojan. As engineers, I don't think we fit that mold of these very quirky kind of robotic type of engineers, the ones that you might see in cartoons and whatnot. And everybody's got so many varied interests, and that's one of the coolest things about the culture that's here. And whether it's sports or it's hiking, or who knows what it could be music, but everybody has multiple facets, and it just makes up for just a very unique student body. And I think that's what makes us stand out even in industry and at an engineering firm. Our students stand out in that regard. And as an anecdote, my sister to this day can't believe I'm an engineer of any sorts, because it's outside of the room I can just turn it off, or outside of the engineering environment, just turn it off and just be me.
And then Dr. Ronney, your academic background.
Okay, so my experience is quite different from that of Professors Gilpin or Radovich. I was actually a student at 4 different universities, none of them being USC. In fact, at one time, or one 4-year period, I was at 4 different universities. I was restless, and so I have degrees from 3 different universities. And then I was a postdoc at 2 different places, and I was on the faculty at another university before coming here in 1993. One thing that really set USC apart from the other institutions that I've been associated with, it's already been mentioned, I'll just mention one more time, is the sense of family and this Trojan spirit. Because I'd been associated with 5 other universities, none of them really had that much of a sense of family, maybe a little bit of spirit, but not really the sense of family and belonging. So when I came to USC and people started talking about this Trojan family, I was like, yeah, okay, whatever. Even Junior didn't believe it. But, I came to found that it was really true. That, to some extent at the other university where I was a faculty member, if you'd accomplished something, people would almost say, well, like, how come you accomplished that? How come you got that award or that grant? And I didn't, almost literally. When I came here and people would, I'd make some accomplishment, people would slap me in the butt and say, hey, Paul, good job, keep it up. My first reaction was, well, what's his angle? Why is he being so nice and all that? But I sort of, that wore off. And so I realized, that in a department like ours, if one person succeeds, that kind of brings everybody out. And so actually took a little bit of an adjustment to get used to that. So one other thing that along the way, so as I mentioned, a lot of my work is primarily in combustion. One of the, my first actually area of research was on combustion in the absence of gravity. So I had experiments that flew on 3 space shuttle missions. I was a backup crew member for the first 2 of those missions back in 1997. So I went through all the training. I didn't get to fly. I would have flown. I was actually back up to 2 people. And if either one of them had some mysterious illness or mysterious injury befall them before the flight, then I would have gone on those flights. So I didn't get to fly, but it was certainly interesting playing space camp for a year and a half. As my wife would say after I'd come home from a week of training, she'd say, so did you have fun playing with your little astronaut friends? So, but it was quite an experience to see things from the operations side. What we do Here, it's about as far from operations. We're always looking for, what's happening 5 or 10 years out. Operationally, what's happening, what we got to do right now, this second.
Great. So for those of you in the audience, please go ahead and throw your questions in the group chat. I will moderate them and try to get them together as much as we can. I'm not certain how many we can get to, but we'll get to as many as we possibly can. We already discussed theory and hands-on, and if you want a number, I give it about a 50-50 split. It's always a little bit different depending on courses that you select, and of course you can always jump in a little bit more on design teams and stuff like that. So keep throwing those questions in. Let's see what we got here. The first question that I'm seeing is aerospace versus astronautical engineering. And what you should know is that we're having an astronautical engineering faculty roundtable tomorrow. And as a follow-up to this session, we will invite you to that, and you can learn a little bit more about astronautical engineering. But one of the key differences is outside of the Earth's atmosphere. How much machine shop access can I get as an undergraduate, and how early?
So I can answer that directly. Machine shop, or you'll have machine shop access the day you show up on campus. And so with our undergraduate fabrication lab in the new bomb makerspace, what we've actually done at the university is we've created these machine shops with the purpose of helping students work on projects. And so the rule in our fabrication lab is it doesn't have to be for a class, it doesn't have to be for something necessarily university related, you just have to be a student. And we can offer machining training, machining time, ability to get a machine and actually make real parts. So in terms of machine access, it could be from the day you show up.
Go ahead, Paul.
Yeah, let me just add that at least in the AME 101 class, it's not only available, it's required. So that's one of the first things we do, is because you'll need that for your group projects and you need to be part of the group, that we put all of our students through a very short, training program, after which they can use the facilities in the machine shop where they've trained.
Great. How difficult is it to switch between mechanical engineering and aerospace engineering? In other words, they probably don't know yet, right? And
Yeah.
This idea of overlapping curriculum is probably not understood. And I think from a prospective engineering perspective, they think they're supposed to have everything figured out before they get started. Can we lay some of that to rest?
Yeah, you don't need to make a decision really until about your junior year. There's one sophomore level course in the aerospace side of things that a lot of mechanical engineers just take because it's flight mechanics, and then whether they use that for aerospace credit or just stay on the mechanical path is kind of up to them. Those students typically have a AP credit or two in their pocket, so they have a little bit of leeway. But aside from just that one course, you can make the transition pretty late. There's really not a lot of pressure in your first year to experience what aero and mechanical engineering are really all about and what you want it to mean for you.
Yeah, and for right now, if you're out there, you've been admitted to a specific program, you know what you've been admitted to. You should recognize that as an engineering student at USC, if you want to switch to any other engineering discipline, you can at any point. You're not locked into your major. And so my recommendation is go with your gut. Go with what sounds most interesting to you to start in an introductory course. And that introductory course will actually be much more revealing about whether it's the right fit for you. And if you wanted to shift, you definitely can. And specifically within aerospace mechanical, as Dr. Radovich mentioned, that switch happens quite commonly as you go throughout your years. I know students that have made some pretty significant changes, and there isn't a hard and fast time. So don't worry too much about that. Can we talk a little bit about robotics? Oh yeah, sorry, Paul, go ahead, sorry.
Yeah, so just a quick anecdote. One year, I had a couple students come through my lab, prospective students. They agreed to accept USC's offer on the condition that they could work in my lab. So Louise Yates, who was in charge at that time, phoned me up and said, will you take on these freshmen in your lab? And I looked at their record and said, yeah, okay, I'll take them on. So they came and they're all bright eyed, bushy-tailed, coming to my lab. Within 6 weeks, not only had they transferred out of my lab, they transferred to another department. Hopefully it wasn't because, of anything that I turned them off to mechanical engineering. I like to think it's because they found what was really right for them. And I'm fond of telling students, sometimes students will come to me with their, tail between their legs saying, well, I kind of decided I'm really not, interested in mechanical engineering as much as I thought I was. I'm really interested in, civil engineering, or interested in art history or something else. I say, look, no need to apologize. This is a university. The root word is universal. that means try everything. And so if you don't figure out what you're really interested in, what you're really passionate about here, when exactly are you going to? As just one little follow-up, I say that I think the most underutilized resource on campus, I'm sure this is true at every university, wherever you go, is faculty members' office hours. Not just if you're in the class, but especially if you're not. Every faculty member loves to have people come to their office hours, people who aren't just asking, how do I do problem 3 on the assignment? Who just want to talk about something they know about. As I say, for example, if you're interested in an 18th century French author, there's probably somebody on campus who's an expert on that author. Go and talk to him or her, get their perspective.
And to be clear, the question just popped in is, what about aerospace, to switching between aerospace and astronautical? To be clear, it's switching between anything in engineering. And so if you're starting out in computer science and you want to go to aerospace, you can do that. Vice versa, aerospace, astro, electrical, biomedical, students are switching across the board. So don't worry. Again, flexibility is key and to being successful in engineering. So we're not locking you into that program. Your first semester is going to really kind of give you that sense of what's right for you, and you're going to be engaging in a lot better sense. So I think that's a key difference. And then that goes into another question where students are asking in different ways here, which is what makes USC specifically stand out against other universities? There's specific call outs here to Georgia Tech and Duke, but I'll call it out across the board. I mean, we're a top 10 engineering school, and our students are looking at all those other top 10 engineering schools. How do we differ?
I think that's easy. Just when you meet a USC engineer in the workplace, you see that they're well-rounded. They have varied interests in addition to being good at engineering. So that's my experiences from actually working with people. I never worked with someone from Duke, but people from Georgia Tech. I don't know how else to say it. I could tell they were from Georgia Tech, but there's just something special about the USC Trojan.
I'll also say that USC's co-location, especially in the aerospace field, co-location with so much of the emerging industry and so much of what is currently on trend in the aerospace field means that our alumni network is plugged into that. It means that our professors of practice and lecturers are plugged into that. Our professors are plugged into that. And USC is an integral part of that ecosystem, which gives a unique perspective of education of not only do you have subject matter experts teaching these courses, but it's subject matter experts who are experiencing in real life what you'll be using these tools to build. And it gives us a unique perspective on what do we want to teach? What do you want to teach students so that they can very easily plug into these emerging companies, these emerging businesses, et cetera.
Yeah, the surrounding opportunities here for work and research once you leave USC are just, there's so many, and it's made me wonder, how do other universities do it? Like, especially the ones that are, let's say, in the middle of northern Indiana, for example. How do they connect their students with Lockheed Martin and Florida or wherever they end up going? It seems like a heck of a challenge, and I think we not only have it a little easier to connect, but we really get to stay in tune. We have so many people that graduate and in their first couple of years continue to come to our Monday meetings for design teams just to continue to transfer knowledge, and it just keeps the ball rolling. It's really cool.
And also a plug for Los Angeles itself. As someone who never imagined I would build a life in Los Angeles, I will say that this city has everything on earth. Whereas some places, personally where I'm from, I'm Pacific Northwest. Pacific Northwest has a great Pacific Northwest culture. If you're into it, that's amazing. But if you're not into it, there's not a lot going on. Whereas Los Angeles itself is so dynamic, so large, and so vast that everything exists there. You just have to go out and find it. And so it's pretty amazing.
Sorry, I spent the first 3 years gearing up to leave Los Angeles, just plotting my next plan, my next plans, or where am I going to go next? And I've spent the last 18 years wondering what on earth I was thinking during those first 3 years I was out here, because this is definitely the place to be for me.
Paul, you had something to add?
Yeah. So in terms of USC versus other schools, I think we've said enough about the Trojan family. That's the one thing I always say is number one. Say, well, it's not an academic matter. All the places that are mentioned, they're great, schools academically. But besides the family aspect, one of the things, and it kind of goes along with that, is our size. Compared to like Georgia Tech, their combined aerospace and mechanical departments are almost as large as our entire engineering school. So there's certainly the matter of size. I think also we're extremely focused on teaching the students the fundamentals, things that will persist, that will be important, not just when you graduate, but 10 or 20 or 30 years from now, as opposed to some universities, I'm not going to name it in particular, that are sort of more focused on, okay, so how can I train this student for the job today? I think USC does a very good job of training students, not just for that, but also for the jobs that will be there 30 years in the future. One thing I also wanted to mention along the lines of our connections to industry and such. Some of my best undergraduate students, I have a lot of undergraduate students working in my lab, and some of them I say, really, you should go into graduate school. You know, tell me what school you want to go. You want to stay here, or you want to go to some other engineering school for graduate study. Tell me where you want to go. I'll call up people I know there and say, hey, you should really check out this student, him or her. I'll write letters of recommendation for you for admission, also for scholarships, etc. And a lot of them say, well, thank you, but I really want to go to SpaceX or one of the other aerospace companies. I mean, I can understand that and to accept that, but we do, I think, a great job. I mean, it's almost like we should have a shuttle. I think the first Hyperloop should actually be between SpaceX and USC, because we're just sending safe as possible there. Whenever I go visit, I walk down the hall and say, oh hi, I haven't seen you in a while. Oh,
Yeah.
Oh.
Yeah, it's definitely extended USC campus down there at SpaceX. Now, we've got a lot of questions that we're not going to be able to hit, but I'm going to touch on a few of them really quickly in lightning round mode. And then I'm going to come back to the faculty to close us out with one last question, and I'll give you the preview of it now, guys. What advice do you have for students as they're going out, as they're going to end high school and going on to start to college? So think about that for a second. I'm going to handle some questions here really quickly. Kevin, in regards to financial aid, I recommend you talk to the financial aid office. I can't give you a number. No one can give you a number, but they can give you an average when you're dealing with loans and financial aid. But talk to the financial aid office. It's a very personal decision, something that we probably shouldn't discuss publicly. When you're talking about, a lot of you are asking about taking different classes and minors and double majors. Yes, you definitely can do that. We're going to help you do that. And that's definitely a topic we cover in our Viterbi keynote. If you haven't attended a Viterbi keynote session, we run them on Tuesdays. Our next one is this coming up Tuesday. Please register for that. It's in your admission portal. And that's where I talk much more at length at the school at large. But this session was specifically focused on the discipline of aerospace and mechanical engineering. There's a lot of questions about what skills do you need to have before you get here, or what should we do the summer before you come? And in general, don't do anything, relax, enjoy. You have the skills. That's why we admitted you. We're going to teach you the things that you need to be taught when you get into our undergraduate courses. So just realize that that's what we're going to be doing. And then Paul, go ahead. You have something, Joe?
Yeah, just one thing along those lines is that what I see in my intro to mechanical engineering course, a lot of people would say, oh, well, they need, to really have the strongest possible math skills. From my perspective, at least for the course that I teach, it's really physics that's more important. When I see students having trouble in my freshman class, it's not because of their math skills. And that's in part because I don't cover a lot of high-level math, or I don't need a lot of high-level math in this course. But really just a really solid understanding of basic physics that you've all learned in high school.
Great. Yeah, percent of students going into the workforce on average, typically in our graduation surveys, it's nearly 3/4 are going straight into the workforce. That's the average of our last 3 years of graduating classes. And the remaining are usually the majority of those are going on to graduate school. There's a small percentage that go into what we call service areas, which is including military service, Teach for America, Peace Corps, AmeriCorps, et cetera. It's usually a 1 to 3% on each individual graduating class. So advice you have as students are going on to college, advice you have if they're starting at USC. What advice do you have for our incoming students?
For the summer, relax. And when you get here, just be prepared to work and get to know us, get to know every one of your faculty, go to their office hours, as Paul Ronney mentioned, not just to ask about question number 3, but to talk about whatever interests you. We really want to get to know you, where you're from and where you're planning on going, and how we can help you get there. And I think that's what will really round out your experience here at USC. So just put an emphasis into doing that. And we're all here. and happy to help you make it to the next level.
I would just add to that, try everything. Come here with an open mind, just try everything. As I said, if you don't figure out what you're passionate about now as an undergraduate, when exactly you're going to do it. The other things I would say is go to faculty members' office hours. My suggestion is that you pick 2 extracurricular activities, one that's related to your major and one that's totally different from your major. Make this a whole university experience. It's not strictly about the academics. We like to think that's the key part, the most important part, but make sure you make it a whole experience.
And to mirror that, I would say yes, try everything. The point of coming to USC is to broaden your horizons, broaden your world. That's absolutely what happened to me. And think about what you're interested in. Think about what makes you excited, what you want to work on. You come to USC, and I guarantee there's going to be people that are interested in what you care about. And if there's probably already a club for it. If there isn't, USC gives you the ability to start that. It's an amazing place to explore the world, how to become a good engineer, and 100%, no matter if it's at USC or somewhere else, as soon as you get involved, get hands-on, work with hardware, experience things, overschedule yourself, make sure that you're actually out there doing stuff, because that's where you're going to get all that learning, you're going to get practical experience, and you also have a lot of fun too.
Absolutely. Well, again, I thank every one of you for taking the time to talk with our incoming students. We had a great audience here today. We will do our best we're going to post this video up, and we're going to post the audio of it up to our podcast. And so if you missed any part of this, we'll get this up and share it so you guys can review it. And we're also going to be posting our other academic departments as well, so you can get to know even more faculty that are out there, as we're doing a few of these every couple days. Once again, thank you very much for joining us. Again, congratulations on your admission. It's a pleasure to have you here. Paul, you want to jump in?
Oh, no, I was saying bye.
Oh, you say bye. Okay,
saying goodbye to
Yeah. Thank you so much, everybody. We really appreciate it. Remember, May 1st is that National Candidates Reply deadline. And if you haven't attended the Viterbi keynote sessions that I host, where we talk a little bit more about the school in general, we're going to have those on Tuesdays. Please see that. If you got any questions for us, email us at vadmit@usc.edu or give us a call. We have a mobile number now where we're all answering from home, 213-600-9919. Again, that's 213-600-9919. Happy to chat with you. Really appreciate it again. And I'm going to say, I would love to keep you on faculty to debrief, but when I close this whole thing, it's all going to go away. So I'm going to say goodbye to you now. Thank you. Yeah, fight on, everybody. Have a great day. We'll see you.